Hey everyone, this is Josh with a fun cybersecurity and software development tutorial for you today. In this video, we'll be talking about 3 common types of software vulnerabilities, particularly relating to the poor handling of user inputs. Each of these vulnerabilities we're going to discuss has its own educational demo available on the Chain Tutorials GitHub. So you can actually read the code, see where the vulnerabilities lie, and interact with these vulnerable bits of code and see how they work. For each of these examples, we're going to give some context as to how these vulnerabilities occur, talk about the specific demos and how they work and demonstrate these issues, and also talk about some steps that we as software developers and cybersecurity professionals can remediate these. So the first type of vulnerability we're going to discuss is the path traversal vulnerability. So for context, these usually occur on backend or middleware parts of web applications. Typically when you visit a website, you're requesting a URL, and that will tell the web server to either serve up a particular static file or will tell code on that server to process that URL and then return the requested information dynamically. So what this means is if you visit, for example, the index.html page of a website, the web server will serve up the index.html file on that server. If we're talking about a dynamic web application, it will process that URL and the code will serve up the information that you request at that particular URL. For example, what you might see in REST APIs. Now, when we talk about navigating the file or directory structure on any system, we need to talk about how you can move backward and forward in that structure on the command line or in code. As we know, we can have folders nested within each other in most file systems. And you can navigate forward and backward using the / character, which tells you to look forward in the directory structure. And in particular for path traversal vulnerabilities, the / character, which allows you to move backwards in the directory structure. So where a path traversal vulnerability can occur is when the code mishandles requests for a particular file in that web server, or a particular file that the dynamic web application is processing. Typically, when we're talking about a web server, we have what is called a web root. For example, on Linux servers, this is often /var/www. This web root folder will contain all of the code and information that the server can return. So static pages like HTML, style sheets, and JavaScript. And typically, a web server is only supposed to serve files from within that web root directory and its subfolders. A web server typically is not going to allow you to arbitrarily read any file on that server system, because there's also lots of private system files, things like TLS certificate keys, or the system's password file that contains the password hashes for the administrative logins. But a path traversal vulnerability throws that restriction out the window. So the particular demo I have for this is called Path Prowler. This is a simple Python backend application that takes a database file name request in the URL that you visit, and in its legitimate use will allow you to view databases of vulnerabilities or malware instances in either JSON or CSV format. But maliciously, you can give Path Prowler a path that moves back up the directory structure outside of the web root and serves up private files. Path Prowler simply takes the file path that you give it, and in relation to Path Prowler's main web server directory, will either serve you a legitimate file that it's supposed to, or, unfortunately, a file outside of the web root. In this particular example, I have a sample TLS private key. Now, if you're not familiar with TLS, this is the technology behind the HTTPS that you see in your browser. This encrypts traffic between the server and the client. So, other than some basic metadata information, all of the communication between you and the website you visit is encrypted, so an eavesdropper can't access that information. But in this case, if you give Path Prowler the // towards the private key, which is supposed to be outside the web root, it will actually happily dump out the private key information for you. So this means that if you're an attacker, you can now eavesdrop any communications between users of this website and the server, which is a really bad vulnerability. So how do we remediate something like this? Well, there's a couple simple ways that we can prevent path traverser vulnerabilities. The first is to use a type of safe path processing. So this is essentially a form of an allow list. Your code will only validate and allow file paths that are within the web root directory. As well, you could do some escaping with the characters in the URL so that it won't actually interpret / and .. as part of constructing and processing the path. So those are a couple simple ways that you can prevent this type of vulnerability. Now, typically, if you're not developing your own web application like Path Prowler, any legitimate web server software that you install will already have this restriction in place. So if you're simply serving up a static website with HTML and JavaScript and CSS, you don't have to worry about, for example, Apache accidentally allowing attackers to request files out of your web root. This is mostly applying to code that we as software developers would write for our own web application processing of file paths. So our next vulnerability is one called cross-site scripting, or XSS. This applies to front-end web applications, typically written in JavaScript. So when we talk about a typical website, we generally have the markup of the page, which is HTML, and that defines the structure of the page and the actual content. We have style sheets, which tell the browser how to render the appearance of that page. And then we have JavaScript. Now, this is what allows dynamic things to happen within the web page on the client side. So this is code that actually runs within your web browser when you visit an interactive web page. There's an upside and a downside to HTML and JavaScript. They are very, very flexible, which allows us to do all the sort of creative things you see with interactive websites. But this can be very problematic because JavaScript and HTML will allow you to do a lot of things that might seem unintuitive if you're coming from a more general purpose application language like Python or C++ or Java or C#.NET. One of the issues is a web page will always process script tags in different ways, and script tags are what tell the browser to include a script file or to execute code that is directly within that script tag. And so what can happen if you don't properly handle user inputs like those from URLs or text boxes or other sort of submission forms is that the page can potentially execute malicious scripts that are provided by the user. And those would be actions that the original developer of the web page didn't intend to run. So in particular, I have a demo of this called XSS Adder. Now this is a sample JavaScript-enabled web page that takes a user ID in the URL and generates a user deposit address for a cryptocurrency service or exchange. It's just a simple sample address in this case. But what can happen with this demo is it does not properly escape any kind of script inputs that you put in that user ID field in the URL. So we can trick the client's web browser into executing a malicious script that replaces the intended user deposit address with that of an attacker's. So if instead of providing a numerical user ID in the get parameter for user ID in the URL, you can insert a specially crafted malicious payload that will replace the generate deposit address function in the JavaScript with that of an attacker's. And this specially crafted malicious function will always give the attacker's crypto address. So theoretically, if you could trick a user into navigating to a URL with this vulnerable malicious payload, they could send their cryptocurrency straight to an attacker address instead of the intended one. And with cryptocurrency, transactions are irreversible. So that user would be out of their money with no recourse, and it would be in the hands of the hacker. So this is a very serious vulnerability. And you might be thinking, well, this is code that runs within a web client. How does it matter if somebody puts a malicious payload in their own browser? Well, think about phishing attacks. Again, all we need to do is to trick a user into navigating to a specially crafted URL in this case. And people click on links all the time from things like emails. And don't look closely at the URL because sometimes they're long and appear to be full of garbage. So in this case, you could send a phishing email out with this malicious URL in it, and that would lead to the real cryptocurrency services website, right? It's not leading to a phishing clone, it's leading to the real website. But the website itself is vulnerable to unintended code injection, cross-site scripting. So the user would end up navigating to their what they think is their real crypto exchange, but the exchange page's code would be executing the attacker's code and not the developer's intended one that gets the legitimate crypto address from the backend server. So depending on how these cross-site scripting attacks are developed, they can lead to really serious vulnerabilities. Now, how do we remediate this? Well, for one thing, we should always try to escape characters that are user input, because we don't want the page to actually try and render those, interpret those as real script tags. So by escaping that out, you can make sure that if somebody puts script code into an input, the browser doesn't actually try to interpret that as real HTML and JavaScript. You'll end up just seeing some escaped out weird looking text on the page, for example. The other thing, again, is to validate the expected input. So if we're expecting a user ID, which should be a simple integer number, we should reject anything that looks like a script or a floating point number or a string. There's just no reason for a user ID to contain anything other than a number. So we can simply do some basic validation there. Now, our final vulnerability that we're going to talk about is the buffer overflow. And this is a fairly well-known and classic vulnerability in computer science. This typically occurs with lower-level software like applications, operating systems, written in languages that allow manual memory management, typically C or C++. And what happens with the buffer overflow is essentially we're going to overwrite memory belonging to other variables in our code. So when we write variables in our code, the computer allocates certain spaces in the computer's memory, or RAM, to store those variables. And typically that's something like 4 bytes for an integer, or 1 byte for a boolean, or a short integer. And then we get into arrays, which are dynamically sized blocks of memory to store individual characters in order. So what can sometimes happen is if you don't properly handle inputs of variable size, you could potentially end up with an input that overwrites the allocated space for an array and starts to overwrite data in adjacent memory blocks. So for a simple example, we'll talk about ominous overflow, which is my demo here. This is a very simple command line application that stores a secret Bitcoin key, and you can only print that key to the screen if you provide a correct password. So for the purposes of this demo, the allowable character space for the passwords is 8 characters. So you can have an 8 or less character password in order to access your secret. Now this is way shorter than we would want for a real secure password, but just for the purposes of this demo, we're going with 8 characters. And some code in there will, once you type your password in, it'll cache that password in memory. And next to it in the memory structure for our authenticated user structure is a short integer, or a boolean typically thought of, and that will store whether or not we are authenticated, whether we're allowed to access our secret. So when we talk about these in C, which is the language of the ominous overflow demo, we typically think of 0 as false for our boolean. Now C++ has a built-in boolean data type, but C doesn't normally. So we use 0 for false, and we interpret any non-zero values, such as 1, 2, 3, 4, or any other non-zero value that fits in that short integer, as true. So here's what happens in this demo. If you provide an 8 or less character password that is correct, the program will, of course, authenticate you and will say you have a correct password and you're allowed to view the secret. If you enter an incorrect password that's 8 characters or less, as expected, the application will reject you. It'll say incorrect password and you cannot view this secret. It won't print it for you. But interestingly, if we provide an incorrect password that is greater than 8 characters, around 9 to 22 works for this particular demo, it will say you have an incorrect password, but then it'll print out the secret for you, which it shouldn't do, right? You shouldn't show the secret information if you have the wrong password. So, what happened here? Well, in this case, we have the string block of memory for 8 characters for the password. And right next to it in memory, we have our 1 byte authentication boolean, which should be either 0 or 1. Now, if we provide a password that is 9 characters or greater, our code will not handle that properly, and it will write the 8 characters to the buffer for the password, and then it'll keep writing into the boolean for whether or not we're authenticated. It starts putting characters in there, right, which is just the ASCII values. And so now you have a character that overwrote that memory and is typically going to be non-zero, which is interpreted as true. So now the application, as we've overwritten this memory, we've overwritten the authentication byte, and our program will allow us to view the secret even though we provided the incorrect password. This is obviously a very serious vulnerability, and this particular class of buffer overflow is known as privilege escalation. There's other types of buffer overflow attacks that also allow you to do very seriously bad things like execute arbitrary code on the target system. But in this case, the type of vulnerability we're dealing with is escalating our privileges unintentionally, unintended by the developers, intended by us, the hackers, and allowing us to have access to secrets that we're not supposed to. So how do we prevent buffer overflows? Well, there's two ways you can think about this. First is if you do have to write an application in C or C++, and they're great languages that are used for lots of different software, use safe functions that put safeguards in place so you can't accidentally overwrite memory segments. So use functions that enforce the boundaries of length, for example, or always make sure you have a null terminator character at the end of a C string. There are some unsafe functions in the C and C++ standard libraries, and then there are safe functions intended to prevent these kind of vulnerabilities from happening. The other one, although not always possible for every project, is to simply use a language where this type of memory management isn't allowed. So if you don't have to write a program in C or C++, you could use a managed compiled language like C#.NET or Java, or you could even use an interpreted language like Python. Because of the way these languages work, you don't do memory management. It garbage collects memory for you automatically and prevents these types of issues. There's also the Rust programming language, which is compiled and low level like C and C++, but is designed with memory safety in mind. So if you can move your project away from languages that allow these kind of vulnerabilities in the first place, you can prevent these. Again, that's not always possible for your project, so you may just have to consider the use of safer functions. So this has been 3 common types of software vulnerabilities. All of these dealing with malicious user input that isn't properly handled by our applications. I find these super fascinating, both as a developer and somebody that's very interested in cybersecurity. It's really important that we write secure software, because insecure software gives all of these interesting avenues for attackers to get in our systems and interact with them in ways that we don't intend. And thankfully, there is lots of common practices that allow us to prevent these types of vulnerabilities. So again, there are several demos of these vulnerabilities available at the Chain Tutorials GitHub, and a written article that accompanies this video tutorial if you prefer to read in print. As always, I hope you found this tutorial interesting and informative, and thank you for learning something new with me today.